So now that we know what the selection rules are for vibrational spectroscopy, in particular infrared spectroscopy, we'll get to Raman spectroscopy later on in this chapter. It's very similar. We can now talk about normal modes, which is basically what is going to allow us to figure out what are the range of different energy states that are allowed or disallowed, but what are the range of possibilities for vibrations in a molecule. Okay, and so the best analogy for a normal mode, you can see sort of a definition here: symmetry of degrees of freedom derived by considering displacement of Cartesian coordinates on each atom. And there's 3n of these, where n is the number of atoms. There's 3n displacements basically for the x, y, z position. So all of these atoms can move either in the x, y, or z direction. That gives rise to 3 degrees of freedom. Again, those are orthonormal degrees of freedom. Okay, so they can be combined. And so the best analogy for all of this and for normal modes is to think of normal modes as the strings on a stringed instrument, like a guitar. And so each normal mode or each string that you have on a guitar allows you to play a certain note, right? And each note has a certain resonant frequency, just like each infrared absorption or scattering process has a certain frequency. And you can play those notes individually by plucking individual strings one at a time, or you can play a chord, right? You could play 2 or 3 or multiple strings. And so if a molecule is getting blasted by infrared light, it can absorb simultaneously, right, different frequencies of light. And then you can go even further. We'll talk about something called overtones, which is a concept to frequency in general. So musicians use this term as well, where you can actually play, a note a higher up. So that would be like putting your finger down on a stringed instrument and changing the frequency so that it's a shorter path length, so it's a higher frequency. So anyway, what we're going to do now is learn how to derive the normal modes for any arbitrary molecule. And so what we're going to do is we're going to start from all these 3n degrees of freedom, and then we're going to subtract off translational and rotational degrees of freedom, okay? Because those are degrees of freedom that don't give rise to a bond stretching or a bond contraction. And fundamentally, when you have a vibration in a bond, right, when we're doing IR or Raman spectroscopy, we have to have some bond contraction or bond elongation. And so for nonlinear molecules, your number of normal modes is going to be 3 times the number of atoms, 3n minus 6. And the 6 that you're subtracting off comes from subtracting off x, y, and z, and also subtracting off the 3 rotational degrees of freedom. We can call those Rx, Ry, and Rz. If you have a linear molecule, you're going to have one more mode. It's going to be 3n minus 5. And the reason for that is because since now you're just a linear molecule, rotating that along the principal rotation axis, z, right, Rz. So the Rz function doesn't do anything, right? That would just be spinning the molecule in place. But if you spin a sphere in place, it's not really moving in XYZ space, right? Perfect spheres are moving. So 3n minus 5 for linear molecules. So we'll use those 3n minus 6 and 3n minus 5 to kind of check our answers to make sure that we're getting the adequate number of normal modes at the end of all of our arithmetic that we're going to learn how to do. So how do you do this? First, you're going to find how each Cartesian coordinate on each atom transforms for each symmetry operation. That will get you a representation that more than likely is going to be reducible. And so then you're going to have to reduce that. And once you get that representation, that's going to give you the symmetry of all the different degrees of freedom, basically, for the molecule. And so you're going to have to subtract off the translational and the rotational modes in order to just back out the normal modes, the vibrational modes, right? When we say normal modes, we're talking about, again, fundamental vibrational modes. They aren't combinations of two modes. They aren't overtones. And so they're just like the strings on an instrument. So what does this actually look like? Well, basically what you're doing is you're setting up, let's take the example of water. We're going to compute the normal modes of water here. And so you set up a Cartesian coordinate system on each of the atoms. And so we can call those x, y, z, and we can give them different subscripts, x1, x2, x3, etc. And this is fundamentally what gives rise to vibrations, right? It's just movement of atoms. It's bonds contracting and expanding. And so by considering the symmetry of how all these different Cartesian systems can move in space, and then reducing that into sort of their fundamental vectors, you are getting out what is actually fundamental in terms of the normal modes. And so first thing we have to do in almost every problem in this course from here on out is you're going to have to figure out the point group of the molecule you're given. For water, that is C2V. And so if you can't see that very quickly, you definitely need to practice at this point, right? So I've pulled up the C2V character table here on the top left, and we're going to use that to help us. So we have 4 symmetry classes in C2V. And so first we're going to ask the question, with each of these symmetry classes, what is the transformation matrix for these coordinates? Right? So this is very similar to what we did when we were deriving character tables, when we were thinking about x, y, and z. But now we are thinking about the positions of all these coordinates, each coordinate system on each atom. And so that ends up giving us a 9×9 matrix, right? Because we have 9 different x, y, and z possibilities here. So the first one is easy, right? That's the identity matrix. So that's 1s across the main diagonal, 0s everywhere else, because x1 went to x1, y1 went to y1, etc. They all go to themselves. Then we would find the character of this matrix, right? And the character is just the sum of the characters, the sum of the values along the main diagonal. So that's 9 1s, so that gives us a character of 9. So that's a value of 9 in our reducible representation for all of the different degrees of freedom of the atoms in water, okay? So we're going to carry on here and do this for the different symmetry operations. So we have C2. So C2, that's 180 degree rotation going through Z1 here. That's the principal rotation axis. So you can think about what's going to happen. Well, first we're asked what's going to happen to x1. X1 is going to spin 180 degrees and it's going to turn into negative of itself. Y1 is going to do the exact same thing. Y1 goes to negative Y1. Z1 doesn't change because you're spinning it from Z1 basically. So Z1 goes to Z1. X2 now is going to go 180 degrees and go all the way around and spin into negative X3. So that's what this is showing. Y2 is very similar, spins around, goes to negative Y3. Z2 is going to spin, go into Z3, and X3 basically does the exact inverse. X3 goes to negative X2. You spin it, right? It's going to go over there. Y3 is going to go into negative Y2, right? And then Z3 is going to go to Z2, okay? So from this, then you can come up with this 9×9 matrix that satisfies all this. And we would find the trace of this, which is -1 plus -1 plus 1 plus all these zeros. That gets you -1. Great. Something that you'll notice is that okay, what values actually contribute to the character, right? The character, that -1 number at the end right here, that's what we care about, right? That's all we need to solve this problem. And so that means we only really care about the characters on the main diagonal. What you can see is that this -1, -1, and 1, that came from all the Cartesian points, x, y, z, came from x1, y1, and z1 on oxygen. And what was special about oxygen, when we rotated it, did a C2, it didn't move, right? But the hydrogens, they moved, they switched places. And when they switch places, their Cartesian coordinates also switch places, which is why their values are these off diagonals. So the ones that didn't move, the atoms that didn't move, had values of 0. They didn't contribute to the character or the main diagonal of this matrix, right? Only the stationary atom did, which in this case was only oxygen, okay? So we could go on and solve the problem this way, but we're going to use this sort of clue here to design a shortcut way of figuring out the normal modes. But I wanted to show you where this comes from. And you could solve the problem like this. It would just take you a long time, and you're doing extra work figuring out these off-diagonal components that you really don't care about, okay?